So in this video, we're going to talk about the method of undetermined coefficients to help us solve a higher order differential equation. So the idea behind the method of undetermined coefficients is to come up with an educated guess about what that particular solution looks like. So let's say we have a second order differential equation. And we have some function over here on the right hand side. We're saying that for this to be satisfied, whatever this particular solution is, we should be able to take first and second derivatives, substitute them in, and get whatever that function is when we simplify that left-hand side. So this method allows us to create an educated guess based on what that function looks like. Now, it works really well if we have coefficients on the left-hand side, if we have a constant on the left-hand side, or a polynomial, or an exponential function, or even sines and cosines, or any combination of those things above. So, just to kind of give you an idea of what's going to happen here. Let's say we have something like this. Well, first off, if this guy were equal to 0, that would be a homogeneous differential equation, and we could solve that using techniques we talked about in section 4.3, where we came up with that auxiliary equation and solved it. But now, that would give us what's called a complementary solution. But now we want to find that particular solution because this is a non-homogeneous differential equation because it's equal to e to the x and not equal to 0. So we're asking, what kind of functions could we possibly plug in for y, take the derivative and the second derivative of, and give us an exponential? Well, a good thought would be, let's try an exponential function, like some constant value times e to the x. And that's the whole idea behind this method. It's coming up with an educated guess about what that function is going to look like, take derivatives, plug it in, and then we're going to do something really similar to what we do with partial fraction decomposition, where we compare coefficients on the left and on the right-hand side. Okay, the same thing would be true if we were looking at something in terms of maybe sine of x. Well, this is what makes it non-homogeneous. So a good thought would be maybe we can try a combination of sines and cosines. Why would we want to try a combination of sines and cosines? Well, remember, we're substituting something in for y, but we're going to substitute in for y prime and y double prime also. If I take the derivative of the sine, I get the negative cosine. And if I want that guy to cancel out somehow, because I want the left-hand side to be equal to just sine of x, then I need a linear combination of sines and cosines so I can eliminate those cosine pieces. So a good educated guess for this would be to try using some multiple of sine of x plus a multiple of cosine of x. So we're looking at that linear combination of those two. So how can we come up with what this solution is going to look like, or what's a good educated guess? Well, there's a table I want to show you down below. And this gives you, for particular solutions, a good idea of what to try to see if you can perform this method. So let's say we have a constant like 1. Well, our y of p that we're going to try would just be the value a. We can write any constant in terms of a. If we have a linear function, we can write it as a linear function ax plus b. Quadratics, we could try ax squared plus bx plus c. Now I want you to notice this particular quadratic does not have an x term in it. Remember, our goal is to... I'm just using this example here. Let's say I had a quadratic like 3x squared minus 2. Our goal is to be able to take derivatives of our educated guess, substitute it in, and work this out so that we figure out what our A, B's, and C's are. Just because I don't have an X term in here doesn't mean when I take the derivatives, I won't have to eliminate an X term in here on that left-hand side. So that's why we need that X term, even though this guy doesn't have one. And if it turns out we don't need it, then we'll end up just getting a 0 for that coefficient that's in front of X. Oh, the math will work itself out. So if we have a cubic, we could write it out as a cubic. If we have the sine of 4x, we could write it as a linear combination of sines and cosines of 4x. Okay, notice you have to keep that angle the same there. If we have cosine of 4x, we're still going to use that combination of sines and cosines because we know when we substitute in and we're trying to account for all the different possibilities that could happen. Exponential functions, if we have e to the 5x, we could write it as ae to the 5x. And then if we look at these are combinations of everything that's above there. What if we have a linear times an exponential? Then our educated guess would be a linear times an exponential. What if we have a quadratic times an exponential? Well, our educated guess for y of p would be a quadratic times an exponential. And you can see how that's going to play out throughout the rest of it. We have an exponential times sine of x. Then we would have an exponential times the idea for sine of x, which would be a cosine of 4x plus b sine of 4x. And if you were to distribute that, you'll get this piece. The same thing would be true if we have a quadratic times an exponential. You can see how all that's going to distribute out. And if we have a linear times an exponential times a cosine of 4x, we're going to have a linear times an exponential times a cosine plus a linear times exponential times sine. So let's start looking at a few examples, and we're going to start with example 1. So we have y double prime plus 4y prime minus 2y is equal to 2x squared minus 3x plus 6. So your first step to solve something like this is to figure out what that the associated homogeneous differential equation is going to look like and solve that. So in this case, our associated homogeneous differential equation is y double prime plus 4y prime minus 2y is equal to 0. So that's going to give us m squared plus 4m minus 2 is equal to 0. We want to solve that. This one does not factor. So we're going to use quadratic formula. So we have negative 4 plus or minus the square root of 24 over 2. 24 is the same thing as 4 times 6. So we have negative 4 plus or minus 2 square root of 6 over 2, which is negative 2 plus or minus square root of 6. So our complementary solution is the solution to the associated homogeneous differential equation, which is going to be C1 times e to the negative 2 plus square root of 6x plus C2 e to the negative 2 minus square root of 6x. And now we want to figure out what that particular solution is going to look like. So if we examine this right-hand side here, we have a quadratic. So a good educated guess would be another quadratic. So let's use ax squared plus bx plus c. But when we take derivatives and we substitute those derivatives in for here, we're then going to compare coefficients on the left and on the right-hand side. And you'll see why that's a good guess in just a second. So let's find the first derivative. And then the second. So now we're going to substitute into that differential equation. So we had y double prime plus 4 times y prime minus 2y and that's going to be equal to that right-hand side, that g of x, which is 2x squared minus 3x plus 6. So I'm going to do some distributing here. So if we look at the left and the right-hand sides, notice we have coefficients in front of x squared, coefficients in front of x, and then constant terms. So we're going to compare what's going on the left and on the right, just like we do with partial fraction decomposition. So I'm going to look at x squareds first. On the left-hand side, we have a minus 2a times x squared, and I'm just looking at the coefficients. I'm not going to put the x squared in. On the right-hand side, we have a 2x squared. So that tells us that a has to be equal to negative 1. Now let's compare coefficients of x. We have 8a minus 2b, and that has to be equal to minus 3. Now we can substitute in what we know. We already know a. This one's going to be a simple system to solve. So we have a negative 8 minus 2b is equal to negative 3. So negative 2b is equal to 5. So b has to be negative 5 halves. And then if we look at the constants, I'm going to use a different color. We have 2a plus 4b minus 2c is equal to 6. So let's do our substitution. We know that a was negative 1, and we know that b was negative 5 halves. So we have negative 2 minus 10 minus 2c is equal to 6. So negative 12 minus 2c is equal to 6. Minus 2c is equal to 18. C is equal to negative 9. So our particular solution, remember it was ax squared plus bx plus c. Our a was negative 1. Our b was negative 5 halves. And our c is negative 9. So let's talk about what the final solution is going to look like. The final solution is always going to be the complementary plus the particular solution. So for us, our y is going to be that complementary, which was c1e to the negative 2 minus square root of 6x plus C1e to the negative 2 plus square root of 6x. And I may have had those transposed in the other one. It doesn't matter. You can add in any order. Plus this particular, which is minus x minus 5 halves x minus 9. So let's look at another one. We have y double prime minus y prime plus y is equal to 2 sine of 3x. We want to solve the problem. Our first step is to solve the associated homogeneous differential equation. So our associated differential equation is y double prime minus y prime plus y is equal to 0. Auxiliary equation would be m squared minus m plus 1 is equal to 0. So if we solve that using the quadratic formula, it can be negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So we're going to have 1 plus or minus the square root of negative 3 over 2, which is 1 plus or minus I square root of 3 over 2. So our complementary solution is going to be C1e to the 1 plus I square root of 3 over 2x plus C2 e to the 1 minus I square root of 3 over 2x. So you could think about factoring that x through to both of those pieces. Same thing over here. So we would have, and I'm going to write it out, C1 e to the 1 half x times e to the I square root of 3 over 2x. And then same kind of jazz going on here. C2 e to the x over 2 times e to the negative I square root of 3 over 2x. And notice we could pull out an e to the x over 2. And that's going to leave us with C1 e to the I square root of 3 over 2x plus C2 e to the negative I square root of 3 over 2x. Now we can apply Euler's formula. So we're going to have C1 times, this is cosine of square root of 3 over 2x. Plus I sine of square root of 3 over 2x. And then we have plus C2 times cosine of negative square root of 3 over 2x. Plus I sine negative square root of 3 over 2x. Remember, cosine is an even function, so this is the same thing as cosine of positive square root of 3 over 2x. So then if I have a constant times this cosine plus another constant times this cosine, then I just have another constant, I'm calling it C3, times cosine of square root of 3 over 2x. Now, could you use that same kind of thought here for those sines? We know the sine of negative square root of 3 over 2x is, well, sine is an odd function, so that's equivalent to the negative I sine of square root of 3 over 2x. And then combining those two sines, we're going to get a new constant, call it C4, times the sine of square root of 3 over 2x. So there's our complementary solution for this particular problem. Now let's analyze that particular piece. So in this case, we had a 2 sine of 3x on that right-hand side. That's our g of x function. So it would make sense to think that our particular solution would look like a combination of sines and cosines. Since this is a second order differential equation, we need to take first and second derivatives so we can substitute in. First derivative, we're going to have negative 3a cosine of 3x. This is a u substitution. Plus 3b sine of 3x. And second derivative. Derivative of the cosine is a negative sine. Okay, hold on. Let's be real careful here. Derivative of sine is positive cosine. Derivative of the cosine is the negative sine. Let me just double check signs here. So the derivative, just reviewing, of a sine of 3x. Derivative of the sine is cosine, so that's going to be 3a cosine 3x. And then derivative of b cosine 3x is negative 3b sine of 3x. So now let's take the second derivative. The derivative of the cosine is a negative sine. Remember, this is a u substitution, so then we're going to have a 9 on the outside, not a 3. Derivative of the sine is cosine, so this is going to remain negative. So now we have everything to substitute in. So our differential equation was y double prime minus y prime plus y and that's equal to 2 sine of 3x. So let's simplify some things. We have minus 8a times the sine of 3x minus 8b times the cosine of 3x minus 3a cosine of 3x and plus 3b sine of 3x. That has to equal 2 sine of 3x. So we have sines and we have cosines. So let's compare coefficients. We have a negative 8a plus 3b, and that has to equal 2. And then we have a minus 3a minus 8b, and we don't have a cosine on this side, so the coefficient is going to be 0. So there's our system of equations. Let's do RREF. Just going to type this guy in the calculator. And when I did that, I got negative 16 over 73 and 6 over 73. So then our particular solution is equal to negative 16 over 73 times the sine of 3x plus 6 over 73 times cosine of 3x. So the general solution is the complementary plus the particular. Our complementary was e to the x over 2 times c3 cosine of square root of 3 over 2x plus c4 sine of square root of 3 over 2x. And then we're just going to add on that last piece there. So minus 16 over 73 times the sine of 3x plus, and I'm going to have to go down here, 6 over 73 cosine of 3x. There's just not enough room to write all that in one line in my tablet. Let's see if I can move everything over. There we go. So there's our final solution. Now we could always check this. We could take first and second derivatives of the solution, substitute everything into the differential equation, make sure we have an identity statement there, which means we have the same thing on the left and on the right hand side. This is the solution to this one. If you wanted to verify that, you could certainly do that. So you can see how the process is the same for all of these. Solve the associated homogeneous differential equation using techniques that we talked about with the auxiliary equation. Then find a good guess as to what that particular solution will look like. Find first and second derivatives, substitute it in, compare coefficients on the left and on the right.